Next topic is mutual inductance. We have already discussed the self-inductance, where we have discussed that flux linkages N phi is proportional to current I. That means if we replace this proportionality with a equality, then we have to multiply with a proportionality constant, and this proportionality constant L is called the coefficient of self-induction. And the induced EMF because of the flux change will be equal to minus N d phi by dt, and because N is constant, so it can be taken inside the differential, and we can write it as differential of N phi with respect to time, and replacing this N phi with Li, we will have, because L is constant here, so it is taken out of the differential, we can write it as di by dt. So E equal to minus L di by dt for a coil having the self-inductance L. And to find the value of self-inductance of a coil, we taken the case of solenoid, in which the Maddy field is B equal to mu naught Ni. So flux phi is mu naught Ni into A. Therefore, induced EMF equal to, if total number of turns are N, then it is d phi by dt, and it is equal to minus L di by dt. Replacing the phi here for solenoid, we write minus N d by dt of mu naught Ni A, and it is equal to minus L di by dt, or we can say, taking the constant terms out of the differential, here this I is the variable, all other terms are constant for the solenoid, so we can say it is minus N mu naught small n A di by dt equal to minus L di by dt. Therefore, comparing, we will get L equal to mu naught n into small n into A. Here n is the total number of turns and small n is the number of turns per unit length. So we can write it as mu naught n square A by L, or we can also write it as mu naught n square A L, where n equal to capital N by L. So in this way we have found the coefficient of self-inductance. In the similar way, we can find the mutual inductance or the coefficient of mutual inductance between the two coils. So to find the mutual inductance of the two long coaxial solenoids of same length. Here, this is the solenoid 2, which is the outer with larger radius, and S1 is the inner solenoid with the radius R1, and where R2 is greater than R1. Let the inner radius is solenoid is S1 with radius R1, length L, because length of the both solenoids are equal, and number of turns per unit length in the inner solenoid are N1, or while the total number of turns are capital N1. Similarly, for second solenoid, which is the outer, having the larger radius R2, length is L, number of turns per unit length is N2, and total number of turns are N2. And the current is set up in the outer solenoid, that is in S2, and here current is suppose I2, which changes with time, and because of the change in current there will be a flux change, and because of this flux change there will be a induced EMF in the first coil, that is the inner coil. So flux linkages with the inner coil, that is N1 phi 1, it will be the proportional to the current in the S2 coil, that is outer coil. And if we equate this, then there is a proportionality constant M12. This M12 is called the mutual inductance of the inner coil S1 with respect to the S2, or also called the coefficient of mutual inductance. Therefore, M12 from this expression of flux linkages, M12 I2 equal to N1 phi 1, and this phi 1 is the flux linked with the inner coil. So we can write it is N1, that is total number of turns in the inner coil, and the flux linked with the single turn, that will be the flux because of the outer coil S2. This flux, this field is the B2 and multiplied by area of the inner coil, because we know flux is the B dot ds. So flux, this Maddy field is due to the outer coil, and this area is of the inner coil. This will give the total flux with the inner coil. Hence, this N1, capital N1 can be written as N1 into L, where N1 is the number of turns per unit length, and the Maddy field B2 of the solenoid is given by mu 2 N2 I2 because of the outer solenoid S2, and area of the inner coil is pi R1 square, because R1 is the radius of the inner coil. So comparing the both sides, we will have M12 equal to mu naught N1 N2 pi R1 square into L. Here N1 and N2 are the number of transfer unit length for the respective inner and the outer solenoids. Similarly, if we consider the flux linkages with the outer coil, and it is given by N2 phi 2, where N2 is the number of turns in the outer coil, phi 2 is the flux link with the single turn of the outer coil, M21 is the mutual inductance of the S2 with respect to S1, and I1 is the current in the inner coil, and this current is due to the current I2 which induces this I1. Here we can write also this M2, from this expression we can write M21 equal to N2 phi 2, and this phi 2 can be written as B1A1 because this phi 2 is the flux link with the outer coil, and this flux is due to the current in the S1, that is the inner coil or inner solenoid. So field due to the inner solenoid will be B1, and this field is here. This is important to note that this field B1 is confined inside the inner solenoid. So we have to multiply the area of the inner solenoid to calculate the flux link with the outer coil. So here it is important to note that phi 2 will be B1A1, and replacing this B1 with the magnetic field of the inner coil or inner solenoid, this will be mu naught N1 I1, and on equating we will have mu M21 equal to mu naught N1 N2 pi R1 square into L. Hence we can see here this M12 equal to M21. So this is the mutual inductance or coefficient of mutual inductance linked with the two coils. Here we have taken these coils are the coaxial solenoids, and this value is mu naught N1 N2 pi R1 square into L. M equal to mu naught N1 N2 pi R1 square. Here pi R1 square is the area of the loop of the inner coil into total length of the solenoids. And if the media between the solenoids is a magnetic medium, then in that case we have to multiply this with a permeability, that is mu r, and this will be mu r mu 0 N1 N2 pi R1 square into L. This is the coefficient of self inductance.